Welcome to another GCBASIC demonstration for the 16F175 chip family. This is part 16. We're going to start looking at some memory. So, my little logo, finish. This is part 16, program memory, SAF memory, EEPROM, and data blocks. They're different types of blocks. I'll explain that as we go into it. Please like and subscribe to this video and subscribe to the channel. I'm in it for those particular things. Part 16, we're nearly there. So I'm assuming you've got everything installed, but important in this one is you have your USB TTL, the last part. That you can program it, but USB is attached. Right now you can use the serial terminal. In terms of what's changed since the last tutorial, let me just put that here. I've reconnected, port C6, the serial TTL converter. Okay, so I've got serial communications between this PIC and the PC. Okay, different types of memory we've got. We've got program memory where we put the program, but within that area of memory is also something that's called SAF. And we're going to look at that first. You've got RAM, put data in there, it's volatile, turn it off, and it's gone. And then finally you've got EEPROM. I consider that as a peripheral because it's programmed differently in reality. And you can read and write that, showing you that in previous tutorials, but however, I'm going to show you how you can create blocks of data with great ease. So in terms of program memory, people typically put programs at the top of memory. What I mean by top of memory, it's logical. That's address 0 is here and here. Sometimes you put your program like this, all a big block. Sometimes you put a little jump in, and then your program starts somewhere down here. And that's fine for the old days. That was really good. That really worked well. And you can use what's called program flash memory or PFM direct addressing. It sort of works. You put in address 0 and it will pull back the results. However, you need to put some reference data in. So what you're going to do is you want some reference data. That's data that you can refer to within your program. You could put it here at the top of memory, here at the top of memory, or just beyond the jump. You put it wherever you like. But in here, you can put pictures and other reference data, and quite a lot. Still uses PFM to go and suck it out. Don't advise you to write back to the program of your program area, but you can certainly read and write program flash memory dynamically from GCBASIC code, very simply. However, these particular chips have something called SAF, storage area flash. It's a limited amount of RAM. Oh, so sorry. It's not RAM at all. Of memory that is synonymous with EEPROM. It has the same types of storage longevity. You can put things in SAF and they'll last a lot longer before corruption, before your program memory. But it exists only at the top of memory. It always is in the red position. It's always from the top. And you need to make sure your program doesn't overwrite it. Now, in GCBASIC, we work from the bottom up. Now, remember, this is address 0, therefore that's the bottom. I will put my pen on. This is addresses. This is addresses. This is address 0 here, and therefore the chances of overwriting are quite low. But in other programming language, you have to tell your programmer and your compiler that the SAF area must not be overwritten because it's non-volatile. You want to protect it in terms of data integrity and security. You don't want to overwrite it by mistake. Other types of, I don't know why I've gone the wrong way. Here we go. Other things I'm going to show you is EE data or data blocks. So there is a very simple way in GCBASIC to create a block of data. You don't have to write it in programming terms. You just put it inside your source code and it will automatically put that data within your program. And it will put it in the EE space, in the EEPROM space. But you can also do the same inside of this program memory area, and it will create large data blocks just above your program, and you can refer to it. It's fantastic. Really simple. Both areas can be therefore used as reference data. So what we're going to do is look at how you actually address the program, how you address SAF, how you create EEPROM and data blocks. All different types of storage. So let's see what's running. Nothing is running. Type in GCS into GC Studio and open the PIC16F175xx terminals. We're looking at the IDE whilst I have a sip of coffee. Control B, we're looking at example 320 showing SAF data to a serial terminal. That implies we're going to have the serial terminal up, hence we need the USB TTL converter. And here's the program. I recommend what we do, we close that down with Control B, we bring up the terminal by pressing function key F9, or you can press function key F4 and you'll get a list of things. I'm going to connect to the terminal. I'm connected, and I'm just going to program it to start with, because I think let's see the result, and then we can discuss it. Notice, all shot past. It's in color now, since the last release. So as of this build, it's all in color. So you get red errors, green for success, etc. So it's now a bit more informative in terms of color. So it's programming it, programming successful. And in the terminal, we have got a load of data. Well, let me zoom in in there for you so you can see it. So what we've got, it's put all this from that source program. And what it's going to do, it's going to do a buffer test. It's going to write out some data to the SAF area of the chip. Where is that? Why don't we look? Because it's just written out 20, 2C, 58, 5B, 4, some numbers. And it says that it's read it back to be exactly the same. So something is writing out the SAF memory. And there's a little block diagram here that says block 0 is equal to the values of 2C, 20, exactly what we wrote out. Let's have a look at that. How am I going to do this? PICKit Plus. I'm going to open up the PICKit Plus software. And what we're going to do is read in the whole of the memory. And then I can show you the SAF. This area here is the program. As in that diagram before, that is address 0. But if I come to the bottom, there is 3FF everywhere. But is there? No, look, there's some data in here. So let me look down the bottom. It says here, at the bottom of this programming software, it says HEF SAF data enabled. And I can create and protect blocks of data. 128 bytes, 96 bytes, 64. And they're all different from different chips. So we're looking at the explicit one for this chip. So in here, it's now changed the color to a nice yellow. And it says here, something wrote a byte of data 20 into this address. Something wrote 2C in here and 58. Well, if you look in our little program here, that's exactly what we wrote. 20, 2C, 58, 5B, 4D, and it ends with 63. 63. Notice, this is not clear in the datasheet. The value that you can put in here is only the low byte that is SAF, the byte. Therefore, the 3F, which is the 14-bit value, is always 3F. When you write to SAF, our routines ensure that when you put bytes or words in there, they go in the right place. So let's have a look. We've got some more down here, AF, 5B, FO, because what we actually did, we wrote some more data in as well. Look. We wrote some more data in. We put 4 words in there, FBAF, FBAF. And if we look in here, FB is here, the low byte, and AF is the high byte. It's in the right place. It's in the right order. So some functions are writing to the SAF properly. Let's have a look. Let's have a look how it does this in the source program. Well, we create a buffer, and buffer management in this particular chip is resolved using the GCBASIC functions because the buffer is protected. You can destroy the buffer very easily. But we create a buffer, an array, we put some data in there, and we literally say to this thing, you can forget about all the H serial print, that's just put it on the screen. SAF write block. It says put it in address 0, my buffer, which is the array, and the number of bytes you want to send out. Well, I think that will be equal to 8, and it is 8 because that's what you put in there. And it will then read in the whole of that data block for you, and then it will write it all back out correctly, verifying as it goes. Because if something exists in SAF, it's a block of memory, 128 bytes. If you just wrote back using program memory write, it would destroy the SAF block. So you need to use SAF write block and read block, and that's what we're using. This protects the SAF block. Here we go, read a block, block 0, put it in something called my buffer, the same buffer. Number of bytes is 8, and it then puts it on the screen using the H serial hardware serial print functions. It then does something else. It writes words out for you. So you can write words out into SAF, and it will read in the whole block, update where you want to write your word data or your byte data, and then it will write the block back. How do we do that? Well, you can write in SAF write word or write byte. You give it the address, and it is a slow process. In terms of speed, it is slower because to write one word means we have to read the whole block, understand what address we're putting it into, and we'll put the word in its correct place. The next one, which is address 10, it will read the whole block in, so it is timely. It takes time, but it's fully managed. And this program essentially shows you that on the screen. And all the terminal is doing is going, I wrote out essentially, if I just clear it, let me do a reset so we can see it. Reset it. Come on, hurry up. Why is that not worked? Is it actually power cycling it? I don't think it's actually power cycling it. It's not power cycling it because I'll just reprogram it. Clear that. What we're going to see is the actual terminal now. So the things to look for are the SAF read and write words, etc., and blocks. They're all documented in the help, but this is showing you what's happening. So this program says this is what you'll find. If you had a PICKit Plus, it would look just like this, and we know it does because we've seen that. So in PICKit Plus, we would want to see these bytes all in memory. Remember the 3F? It's not SAF memory. Really important. Use SAF write and read. Okay, let's have a look at something else whilst we're here today. I want you to come into here. Now you've got all the files that have been associated with that project. So I'm just going to go Control F, .gcb, and turn the filter on. 330, show program memory data to terminal. Similar program, Control B, similar program. I've got the similar setup, but this time we're going to use program write, and it's going to write some values straight out to the chip. It's going to write a value of 55, 124, straight out to memory. So if you wanted to write straight into memory, this is the command to do it. If you want to read it back, you use program read, the address, and then the data word. The rest of this program sets up the UART and sets up the terminal so it looks half decent. A lot of this program is really just around putting that on the screen. Let's zoom in on that. It says here that at address 00, I've got 31802805. I should read the memory, shouldn't I, really? Let me do that. Well, that's the jump anyway, so that's the page select. And now you can look at it again. And it is exactly as per what's on that terminal is on that PICKit software. So if we look at address 1F over here, 1F is down here. It should be 00AD. Here we go, 00AD, because the next byte is address 00AD. The one before that is 3081. So we have ways of reading the memory. But what about the top of memory, where we want to put our reference data? This is all like the SAF area. But this does explicit writes. You can lose data in here. You are not writing to it properly with SAF if you use this method. Be careful. SAF area is different. Now, where do we put it? I put it at address 3F F0. 3F F0. 3F F0. I can't even find it. 3FF. 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 Oh, here it is. 05 and 1234. Is that in the is that area the SAF area? It is. If you had SAF data in there, you'd have blown it away. So what you should do in reality is always put reference data ending at this address 3F 7F. For this chip, other chips, you get different mileage. What I've also put in this demonstration for you is how to create data blocks and EEPROMs. I did say I was going to turn about that. So if you want to put some reference data in and you can refer to it as reference block 1, you just say program read reference at reference block 1. It will go and get you some data. So why don't we look for this data here? 5, 55, 54, 53 in hexadecimal. Well, we know it's somewhere in memory. Well, it's sitting. I'll zoom in. It's sitting here. Here's the top of memory. I'm looking for value 55, which is that 3455, 3454, and 53. It wrote the correct values as bytes into memory. Remember, you've only got a 16-bit address on this particular chip, so if you go write in words, you're going to lose your data. You can put them in as words, it will work, but just be careful. Look at the help. In terms of writing out an EEPROM data, look, you can just go EEPROM. This is a string in EEPROM data, 1, 2, 3, 4. 1, 2, 3. I'll put a 4 there because I said 4. Look. It won't be in the program. And then why don't we look at it inside of oh look, we've got a load of data automatically put in here. If I look at as ASCII, it says this is a string. Well, it's done it. It's done it. It just does it. Okay. And then it's gone. This is the EEPROM data, and then it's got 1, 2, and 3. So to write out data into the EEPROM as reference data, you simply use the EEPROM command and end EEPROM, give it a name, and it will go out. You can put other parameters in here, which is the address. So if you wanted to put it at address 16 or 20 hex or whatever you want to put it at, you would just put the address in there, and then if you program it out, it will automatically insert it at that address there. And so if we look at here, all that data was placed at address 0. We can see it there. I'm just going to read it in to show you. I'll read it in, and now it's moved it down to, I'll zoom in, be better. It's now moved it from 0 here to address 20 there. Perfect. Reference data in EEPROM. In here, you've got 256 bytes of EEPROM data. Cancel that. I have no idea what that pop-up was. Okay, that's all I wanted to show you. That's long enough. Me ranting. Next, CLC, whatever that is. Enjoy.